In this video, I'm going to demonstrate how to use a capacity meter to measure voltage, current, power in watts, energy consumed in watt hours, and total measured capacity in milliamp hours. To do this, I'm going to use a power supply to mimic an actual battery. I'm going to demonstrate how to set up the power supply for this first test here. First, I'm going to turn the power supply on, which it'll go through a cycle to start up. And it remembers the last setting. So currently it's set to 12 volts with a maximum of 4 amps. You can adjust the voltage using this dial here. You can also change which digit you want to adjust. If you want to adjust the voltage faster up or down, or if you want very, very fine tune adjustment, you can do that. If you want to switch to current, then you would press that button, and the same thing happens here. You can adjust which digit you want to adjust using the knob and then pressing this knob in. So I'm going to leave it at providing 12 volts at up to 4 amps because that's how I want to run my test. Here we've got the capacity meter set to draw 2 amps, and we can see that the current voltage on these wires is 0. That's because this is not yet providing voltage out. To do that, you press this top button here, and now the power supply is providing 12 volts, and currently there's 0 amps being drawn through the wires. And we can see here we've got 11.99578. It's varying a little tiny bit, but it's not unusual. I don't know if there's going to be really that much voltage drop on these wires with no current, but it's not unusual to be off by, in this case, this looks like a very, very small fraction of a percent. All right, so I'm going to begin the test. The way you start the test is simply to press this button down here. And what that's going to do is it's going to start immediately trying to draw 2 amps. And we're going to see here the actual real-time current that's being drawn. And what this is going to do is going to try to average over time 2 amps. And then we can see over here on the meter that we've got basically about the same amount, roughly 2 amps. It's a little bit higher. Again, things can be off by a tiny fraction of a percent. That's just how devices are. Nothing is exactly 100%. We also are measuring the power, which would be the watts, which is basically current times voltage, which will give you the watts, and then the energy consumed in watt hours, and the capacity consumed in milliamp hours. So if we have 12 volts with a current draw of 2 amps, we'll have a capacity, if run for 1 hour exactly, of 2 amp hours with a energy usage of watt hours of 24 watt hours. So you may be asking, why are we showing less voltage? Why are we showing 11.6 volts versus 12 volts? Well, that's what we're going to cover next. Okay, here I've got my voltmeter set up, and we're going to go ahead and measure the voltage at the power supply. This will be a little tricky to reach in here, but we can see the voltage at the terminals is coming to 11.97, which seems reasonable. And then we're going to measure the voltage here through this one set of wires, which we're going to get as 11.686970. And you'll see that that pretty much matches the same voltage that's on the capacity meter. And that's what these little wires are all about. Basically, these capacity meters are built with 2 sets of inputs. The outside is where the current is being absorbed, and the inside is what's actually being utilized for the voltage. And we can see that here because if I put my voltmeter here, I can see that I'm measuring 11.64 volts, and this is showing 11.6869. But if I put it here, I can see now we've got like the 11.69, 11.7. Okay, I can see we have the 11.69-ish number here. So it's a little higher. If I wanted to see the voltage drop across these two, we can then see it's roughly about 0.011 volts at the 2 amps. So what this is actually measuring is the voltage here, and then all of the voltage drop that is being measured is occurring in these leads here. Now we could actually measure that voltage drop as well. If I put my meter here, we're going to see that the voltage drop across this section is 0.05, 0.06 volts. And we should see something very similar across the negative lead because it's basically the same length of wire, although it is higher, which is surprising to me. So I'm guessing that the negative lead actually has a larger voltage drop than the positive lead, which is pretty interesting. I may add a section at the end of this video to see why that might be. So anyhow, as we increase the current draw, which we do by just pressing this button here, I'm going to change this from 2 to 3 amps. Now we can see that the voltage is becoming less, 0.64. We can also see the current went up to 3 there. So if we measure the voltages here again, we're going to see 11.59 on the current terminals, and then the actual voltage is 11.6263. It varies. Now the voltage drop here, I would expect it to be 50% higher than it was before. And then the same thing probably here, about the same. And then these two here, 0.088. And then this negative one is going to be higher, 0.224. That's pretty interesting. There's something with this negative lead, because this negative lead should have a similar voltage drop as the positive lead. And we'll see what happens when I go to 4 amps. Now, since this is current limited to 4 amps, this voltage may drop, and it may cause the test to end. We'll find out what happens here. So we've got 4, and it's just squeaking by. If I up it a little bit, and why don't we go ahead and try that? We'll try it at the minor digit here, and I suspect that'll cause this meter to actually kick off, because it's going to draw more than the power supply is going to limit. There we go. That makes sense. We're now going to do a timed capacity test. In order to get more accurate results, I've removed the test leads and I've created these little leads here that connect directly to the power supply to get more accurate results. So I'm going to go ahead and reset this so that my capacity is 0. I'm also going to go ahead and change the time discharge by holding down this top button and then pressing it again, and that's hours actually, and then that's minutes. So we're going to go ahead and set this for 6 minutes to run. If I press this top button again, I can also change the cutoff voltage from 2.0 volts to whatever voltage I want, but 2 volts is fine. And then once more it goes into the Bluetooth setting, and then once more we're back to normal. So I'm going to go ahead and run my test now, and this is going to take 6 minutes. As we're getting to the end here, we can see we're at 5 minutes, 54 seconds, 55 seconds. This should automatically kick off at 6 minutes. And there we go. And we can see that the energy consumed is 6 watt-hours, 400 milliamp hours, which is exactly what we've calculated it should be. There is one more feature of this power supply that I wanted to note. It has an overcurrent protection. So what I've done is I've configured the power supply to have a 1.5 amp current limit, and I've set my capacity meter to draw 1 amp. If I press this third button down here, we have OCP, overcurrent protection. So when I start up my capacity meter, I'm drawing 1 amp, which is less than the 1.5 that we had configured. And if I slowly boost this up, you can see here we're at 1.4, which is still under, But if I boost it to 1.5, we've hit the overcurrent protection, and the power supply actually then cuts off the power and stops supplying power entirely as a safety measure, as opposed to limiting the current if you started drawing more. To stop that beeping, you would just press that top button, and now you're all set to start again. Of course, it's turned off the voltage. You can see here there's no voltage on, and we can press it again. If you turn that button off, what you'll see is that as you draw more current, the voltage will come down. One more thing I wanted to look at was, remember we saw that the voltage drop in these leads here was more for the negative than the positive lead? I'm curious about that. If we look here very closely, we can see that the wires crimped into these connectors pretty evenly, so I wouldn't think the issue would be here. So we can look at the actual alligator clips and see how those are attached. So we can see here that this is just kind of crimped on. Yeah, I usually just kind of squished against the side. I usually solder these on. So I'm going to go ahead and let's take a look at the negative one as well. And we can see here that it too is just kind of squished on a bit. So let's do a test. This is just out of curiosity. Okay, let's see if we can just measure the ohms across these. So I'm going to go ahead and try the positive first. I'm going to measure that to this. And according to my meter, we have about 0.3, 0.2-ish ohms, roughly. Okay, now let's try that for the negative lead. That's on the negative. And now we're going to do this way. And we can see we have 0.5-ish ohm. So it's definitely higher. I'm going to go ahead and do a soldering step to solder that wire onto both of these and see if that helps the overall ohms of this. So here I've got my little soldering iron out. It is turned on. And I've got my little helper here. This is really handy, by the way. And I've got my alligator clip set up. A couple things I just want to mention. One trick that I learned a long time ago is if you're ever trying to scramble and you only need one little tiny piece of solder, it helps if you actually wrap some solder around the cord. That way you've always got some available should you need it. For this job, I've got my regular solder roll, so I'm going to go ahead and use that. So basically what I'm going to try to do is I'm not going to take the wire out. I'm just going to try to solder in place. This may not be the best idea, but solder in place this wire that's already on there onto this alligator clip as it is. And the solder should really help and make a good contact. So we'll see how this goes. This is just trying to do something quick and simple, and we'll see if we can get it to actually work. There we go. Now I can see that it pretty much has gone through and connected to the alligator clip. I let that cool off and then I took it off, and now we're going to try the negative. Okay, this one you can see the insulation's actually kind of in the way a little bit, but let's see if we can just make this work. Okay, that looks like it's done. It's decided to melt on there at that point. All right, we're going to let that cool and then we're going to give it a try. So we're going to repeat the voltage test drop, and this time I've got my display so it's a lot more visible. I apologize for that, but since I've already fixed the leads, I can't repeat the test. So I'm going to go ahead and draw 2 amps, which is what we were drawing before, and go ahead and turn that on. And now we're drawing 2 amps, and now I'm going to see what the voltage drop is between the power supply and the alligator clip here. So we got that there, and we got that, and we now see we have 0.049, which is actually less than it was even for the positive one. And it's the negative one that was had the larger drop. I think it was 0.1 or something. So now we're 0.046. That's significantly improved. So this is a really improvement. Just by doing that little solder bit, I improved the resistance or reduced the resistance in the leads that come out of the power supply. So that's something to note, something worth knowing. Crimped-on did not seem to have as good of a contact as a solder connection, which one would think is true. Thanks for watching. Please like and subscribe.